Today, I'm going to present our research group's work on using random testing to harden LLVM. First, let me show you a crash bug inside LLVM we have found for a revision in 2.8. While LLVM was optimizing this loop, it was trying to apply a loop invariant code motion on this piece of code. For some reason, it made an over-aggressive assertion, says this variable whose address is taken on the right side shouldn't be used by the expression on the left side. And you can see this assumption is wrong, and we make our code has made the compiler crash. Next, I'm going to show you some run code bugs we found in the compiler. This one is from a 2.4 revision. It tries to simplify this combination of comparisons into one comparison, but apparently it chose the wrong one to simplify to. And this 2.8 revision tries to fold the whole expression into 0. We took a look of the source code and found the reason is they somehow think this expression is a constant integer, and try to apply a rule shouldn't be applied to. And finally, the run code bug is found in this loop. LLVM was able to say this loop does nothing and try to reduce to the variable directly to the number of iterations for this loop. But somehow it computes the iteration number wrong. It says the iteration is 1. Instead, you can say the iteration should be 5. So those just a few samples of bugs we have found over the last 3 years. From the March 2008 to present, we have found a total of 173 bugs in LLVM. And 170 of them has been fixed already. There are 57 run code bugs and 116 crash bugs, which accounts for 2.6% of overall valid bugs filed against LLVM in the same period. So what do we do? Our goal is to find compiler bugs. Our goal is to find deep optimization bugs inside the compiler. We try to use random differential testing, and we try to automate the process from bug finding to bug reporting as much as possible. The ultimate goal is to make LLVM a better compiler. So what exactly is random differential testing? First, it starts from a random program generator, and you generate C programs. Then you pass it to several compilers, Clang, GCC, or whatever your favorite C compiler. And you compare them at different optimization levels. Then you run the executables. You compare the results. If there's any disagreement among the results, those compilers who produce the minority reports will be sent to the dark house, which means we will find the bugs in the compiler. There's also another kind of compiler bugs we can find by running the random program. That's when the compiler crashes while compiling our program. So for a single random program, you probably will find nothing. But if you repeat this process over and over again, and it becomes very powerful for compiler testing. So that's what we do. And I'm going to describe what we have learned. We first, to evaluate how effective is this random differential testing, we have run an experiment. We use our random generator to generate 1 million test cases. And we pass them, we compile them on x86 machines with LLVM from 1.9 to the most recent release 2.8, those optimization levels. And we try to find the crash errors and run code errors triggered by those test cases. In this graph, the x-axis are the release version of LLVM, And the y-axis in log scale are the crash error percentage of those test cases. So 1% means we found 10,000 crashes out of the 1 million test cases. And we also marked the number of bugs, the number of crash bugs we reported and get fixed for each release. And you can see we constantly are reporting bugs, crash bugs. 2.8 seems to be the least crash compiler from this graph. And we also take a note of those distinct crash errors. We think 2 crash errors are the same if their crash message is the same. And again, we have found plenty of distinct crash errors, with 2.8 still being the best. Now let's take a look at all those run code bugs, run code errors, actually. And the y-axis is the run code error for those 1 million test cases in percentage. So 0.1% means we find 1,000 test case which generate run code error. A run code error means there are disagreements among the results from different optimization levels of LLVM. Now, we have also marked the number of run code bugs we have reported and get fixed for each release version. So once again, we have seen 2.8 being the most resilient for our random testing. So can we draw a conclusion that our random testing has made LLVM a better compiler? Well, we have seen correlations, but the causation relationship is not so obvious. But definitely, we have made our contribution to make the compiler better. Let's let's pay our respect to those people who has put in the effort to fix our bugs. Dan is clearly the champion, fixed 39 bugs, and Chris is the runner-up. And for some people there, we probably didn't recognize your contribution because there are some bugs we couldn't identify who fixed the bugs in the bug database. So there are about 10 bugs we couldn't find who is the fixer. Just make sure next time when you fix a bug for us, leave your name there so we can properly honor your efforts. Now let's take a look where are those bugs distributed. We found there are 10 bugs in the front end. And when I talk about front end, we actually test 2 front end. One is LLVM GCC, one is CNI. We actually found more bugs in the LLVM GCC. There are 61 bugs in the middle end and 67 bugs in the back end. Again, because the record in the database, we couldn't find 35 bugs. We couldn't find the file who is responsible for the fix for 35 bugs. So we couldn't identify which stage they are in. Now let's look at the distribution across source files in LLVM. And as you can see, our random tester can frequently find bugs in some of source files, like the first 2. I don't think this necessarily means the developer did another job for those files. I believe this is because the nature of the work they are doing make it more vulnerable to random testing, especially our random tester. And you guys probably know better than me what these files are and what are they doing. So you can draw your own conclusion. Your guess is as good as mine. Now, given our success to find the compiler bugs, we were wondering if it's because we can cover more program space in the compiler. And we did a measurement of the coverage. So the baseline is the test weight from both CLON and LLVM. and we added 10,000 random test cases on top of it to see how much increase in terms of coverage. Well, it's not as much as we expected. It's, as you can see, for coverage on nouns, functions, and branches, it's almost identical. It doesn't increase too much. So our guess is, at this stage, is because those coverage metrics is not fine-grained enough to reflect the strength of random testing. Now here comes the technical part. How do we do it? There has been many random program generators in the history, and we want to build something different. We want to build a random generator which can generate programs with unambiguous meanings. I will talk about what that means in a moment. And we will also want the ability to check the meaning of the program has been preserved by the compiler. Well, one way of checking is by first summarize the meaning of the program. The meaning is just too vague, so we have to define it some way. Our definition is to compute the checksum of all the global variables at the end of the program, the execution, and dump the checksum. Then we have a test harness will automatically check if the checksum produced by different compilers are different. Let's take a look at some examples where a program could have ambiguous meanings. In this example, you have a program when compiled by GCC, it dumps 0. When compiled by CLAN, it dumps 1. Does this mean there is a bug in one of the compilers? No, because what we are doing in the program is adding 1 to your int max, which is undefined by C standard. So the compilers both of them are correct. Now, here is another ambiguous program. If you have a function called bar, and it has 2 arguments, assign either 1 or 2 to A, those 2 expressions could be valued in arbitrary order. So when compiled by GCC, it will give you 1, and by CLAN give you 2, and both of them are correct because the order of evaluation problem is unspecified in C standard. So essentially, we have to achieve 2 goals when we make this random generator. On one hand, we have to make it expressive enough to cover many C program features. On the other hand, we must avoid any undefined behavior or unspecified behavior at all costs. We have noticed both goals can be, either one of the goals can be achieved by sacrificing the other goal, but to generate expressive code that avoid undefined and unspecified behavior is very, very hard. So we have to make some design compromises. The first compromise we make is we allow implementation-defined behavior in the random code, which means the size of, such as the size of integer, it could be 8 or 16, depends on which compiler implementation you are using. This means we cannot do differential testing across platforms, but this is okay for us because we did most of our testing on x86. The second compromise we made is there's no ground truth in the random code. It means we don't know which values ought to be which variables ought to be which value at the end of execution. There's no self-checking in the code. We just compare the results from different compilers. And the third compromise is we don't attempt to generate term unity programs. So in practice, we found about 10% of our random code will never exit. But we can deal with that with a timeout. So let's see how our random generator is doing on the expressive side. We can generate C features such as arithmetic, logic, and bitwise integer operations on the integer types from byte up to 64-bit integer. We can generate loops. We can generate branch. We can generate function calls. We can have const and volatile quantifier attached to variables, including pointers. And we can generate struct. With some of the struct field can be bit fields. We can generate pointers and arrays. And lastly, we can generate some control flow statements, such as go to, break, continue. There are still a long list of features we are not supporting yet. Some of them are pretty easy to add, but yes.
You said that your differential testing is based on check some global variable.
Right.
And at the same time, you say that the test harness has a timeout of so much. So even if the binaries are exactly the same, the timeout
Yeah.
start at a different point.
That's correct. So in that case, we just throw out the test case because it doesn't exist, so we cannot compare the results. So 10% is something we can accept. We didn't feel the urge to implement them because we already have enough bug finding power. It turns out we can avoid some of the undefined behaviors with extra code in the random program, such as for the use before initialization problem, we can declare all variables with the initializer. And for no pointer, we can just check the pointer before dereferencing. And we can also do the same thing for integer undefined behaviors, such as divide by 0 or send integer overflow. We basically wrap all the integer operations with a wrapper. And the wrapper function will check the operands of a function, your integer operation to see if they are going to cause undefined behavior or not. If yes, they are going to back out. If no, they do the operations. It turns out some undefined behavior are very, very hard to avoid statically, structurally. So we have to have something in the code generator to avoid them statically, such as dereferencing a dangling pointer or the order of evaluation problem. So in the end, we have something like this. On the left side is the code generated engine. On the right side is basically a static analyzer, which does three things: point analysis, side effect analysis, and code validation. So the last thing it does is look at any piece of code generated by the engine and see if it's going to cause pointer undefined behavior or side effect undefined behaviors, and reject the code which will cause the undefined behavior. Some future work. We definitely want to make this a tanker system. So that means anybody who is interested in compiler testing can download the tool and start testing, even though he's not familiar with random differential testing. But our test harness is 7,000 lines of per, and part of it needs to be rewritten to be portable. We also need to improve our test case reduction. Right now, the random generator will generate a lot of redundant code before it generates the real code that will break the compiler. So we need some automatic reduction to get rid of those redundancies before we report the bugs. Right now, we can reduce up to 90% of the redundancy, but that's still much room to improve. We definitely need to support more C features, as we have a long list of not supporting features. We probably will also extend our random testing to other languages. C++ is obviously target. We could also use random testing on other formats, including the intermediate representation of compilers. So for you as developers, we expect you to, we hope you keep fixed bugs we reported. And you can also tell us where do you think random testing might be useful for you? So in conclusion, random testing is powerful. We have quickly found bugs in compilers on virtually all the compilers we have tested, including LLVM and GCC. We have found deep optimization bugs not likely to be uncovered by other means, such as static analysis. We can generate small test cases which can pinpoint to the problem, so the compiler develops doesn't have much trouble to reproduce it. But there are some limitations for our random tester. It doesn't know when to stop. So there's no such thing as exhaustive random testing. Also, the code coverage, as what I have shown you, is not broad enough. So we have to figure out why. We also think compilers need random testing because again and again we have found bugs which couldn't be uncovered by test suite. So we think test suite alone is not enough. Maybe in the future, this combination of fixed test suite plus random testing is the way to go for for compiler testing. I think that's all.